In this session, we're going to run through how to do a chi-squared analysis. And in this type of analysis, we have two categorical variables, and we want to find out if there are differences in the way that the groups are distributed. In a sense, this is a correlation between two categorical variables, right? So we're going to start by opening a script, and this may be a little different, so I'm going to show this. We're going to do open file, and I happen to already have this script on my desktop. And the first thing we're going to do is load dependencies. And this is slightly different here, probably than we've seen before, and we're going to use the pacman package to install and load dependencies. This can be all done in one step. So this first line here just ensures that the pacman package is installed. If it isn't, it goes ahead and installs it. This next line here will install any packages, tidyverse or gmodels that is. It install them if they're not already installed, and then it'll load them. Since they're already installed, it just loaded them. This next line here will check for updates and install the most recent example data from my GitHub account. Okay, next we're going to check out two functions. The first one is a built-in function, part of the stats package, and you can pull up the help for that, and you can see some of the options that you can get for that. The second function is part of gmodels, and that gives you some nice tabular output, gives you some extra information you wouldn't get from the first test there. Okay. Now we're going to take a look at the data set we'll be using today, and that's New York City dogs. And we've seen this one before, I believe. We're going to be looking at two particular variables, breed and dog name. Next, we'll look at a hypothesis, and this is kind of a contrived hypothesis in a sense because I wanted to keep the table fairly small for us. And the hypothesis is that for the top 4 breeds and 4 names of dogs in New York City, the null hypothesis is that there is not a difference in naming among breeds, and the alternative hypothesis is that there is a difference in the naming among breeds. So let's start by visualizing this a little bit. And we can do this by getting a count first of dogs by names, right? And we said here we only want the top 4 breeds and the top 4 names. So we're going to go ahead and grab, well, I guess we'll arrange that by descending. And we don't want that NA at the top because that's not really a dog name, right? And we're going to grab just the top 4 rows. And so this is maybe a new function to you, slice. And what slice does is it just grabs the number of rows you want. Here we say 1 through 4. So it'll grab Max, Bella, Rocky, or Lucky and Rocky, those 4 rows. So let's see what that looks like. And then the last function here is pull, and it grabs just the column we want, which is dog name, and it pulls that into a vector. We'll see what that looks like. So those are the names of the dogs that we want to pull, because those are the top 4, right? We want to do the same for breeds, so we're going to grab a count of breed, sort it, descending. So these are your top 4 breeds. And we're going to grab just the top 4 with slice, and then we're going to pull that variable, and these are your top 4 breeds. All right, so now we have 2 vectors. We have one called DNMS for dog names, and the other is BRDS for breeds. And we're going to go ahead and filter out and grab just those dogs that are in that breed and name that name, right? And we're going to make a new mini data set, or a subset of data. And you can see that there are, let's zoom up here a little bit, approximately 1,500 rows in that data set, right? Now we want to look at that relationship between dog name and breed, and these are 2 categorical variables. So one of the best ways to do this in visualization is to use a heat map, right? So what we need to do is to compute the counts for each of those. So count is a great way. We could have also used group by and then summarize with a length. This is a bit nicer and easier to do. And we can see we have each of the dog names and then the breeds and the counts with those particular numbers. And this is not a particularly nice way. This is tidy, but it's not necessarily a nice way to look up values, right? And we'll look at how to make them more in a crosstab, untidy format. But ggplot2 loves this format, this tidy format, and it's easy to figure out what the variables are. You have dog name, breeds, and then counts. So we go ahead and pass that in as a data set to ggplot2. We tell it that the x and y variables are breed and dog name. We could have been explicit with that if we want. And we also say that the fill, because we know it's a geom tile, we want to fill it. Fill is based on n, so that maps fill to n. So let's go ahead and see what that looks like. That was pretty well for us, right? But I don't really like the default color, so we can change that if we want with scale, fill gradient, and we can specify a low color and a high color of white and red. So let's go ahead and look at what that looks like. And to me, I like that a little bit better. And I also like to get the numbers right on there. So we can actually say, okay, geom text, keep the x and y variables because we want it dog name and breed, but we actually want to also put labels on there. So we need an aesthetic for geom text is label, and we tell it, well, what do we want for labels? Well, we want to put down n. So let's see what that looks like. Now we have counts right on there, and we could change that label size if we wanted to a constant. We could say size equals 4, color equals gray. I don't know, I'm just picking up random stuff here. And I think we could go a bit bigger on that. We could go a bit darker on that. Okay. Could also have done label. Let's see if this works. Label equals breed. Not too useful, but you can see what label does there. So we'll go back to n there for a second. All right. Now it'd be useful to also have these rows and columns as counts, and if we're going to do just one variable and we want to do counts, probably one of the best ways to do that is a bar plot. So we're going to grab just the count of dog names from our subdata set, ny dogs, and we're going to count it and then arrange it by n. And you can see this is in ascending, not descending. And let's actually do descending for a second. It's a little nicer if we want to see it as a table in descending. And then we can go ahead and we'll actually just plot it as is for a second. And yeah, that's good. I'm leaving out that mutate. Passed it on to ggplot2, passed in dog name, and then y is, my y variable will be n, and because I'm passing in an actual value, a number that is, a variable for y, we don't want it to be stat equals count, which is the default. We want it stat equals identity. So we'll go ahead and do that, and we can see our bars are not ordered. So that's not, I mean, it's nice, but it would be a little nicer if they were ordered. So we can do that by specifying our factors levels, right? So we do that with a mutate. And we say up above, okay, dog name, we want that to be a factor, and we already know the levels because we've arranged it on descending, and we say levels equals dog name as well. Let's go ahead and see what that looks like. And now it looks pretty good. If we wanted to flip the coordinates like this, we could do that, but now we see the ordering is backwards, so we might want to get rid of the descending up here. And you can see Max is the most popular name, Rocky is the least popular of the 4. Okay? We also want to get a count of breeds, right? We can do that. We're going to arrange that, ascending on n. Pass in those, we'll turn the breed into a factor, as we just did up above. You can see now it's a factor, and it's ordered. Chihuahua is the first, mixed to other is the last. And we're going to go ahead and pass in breed as the x for ggplot2, y equals n, and of course we'll need stat equals identity because we're giving it a y value. Let's go ahead and view that. And we can see, wow, mixed other is the largest breed. In a sense, it's not a breed, it's just kind of what's left over. All right? So now we have those 3 plots, and we can zoom through and get some pretty useful information about the data set. But we want to know, are these differences here in the heat map, are they significantly different? So is where it has max and mixed and other, is that vastly different than what we would expect there, given the counts of all dog names and the counts of all breeds in those groups? Is the interaction between those two off of what we would expect, right? Or this 27 here for Chihuahua and Max, is that vastly, seems to be quite a bit less than the other Chihuahua names, is that vastly different? So for that, to answer that question, we need a statistical test, right? And we need to get our form into, for this particular test, we do not want tidy format. And we want crosstabs. And here's how you would do crosstabs in the tidyverse world. You do a count of dog and breed, and then you'd go ahead and spread breed out across columns, and you'd fill in by n. So that's what I have here. Spread out dog name, and fill in the values will be n, right? And so we have a data table, or a data frame here, which is in the first column is breed, and you have the dog names, so on and so forth, right? This still isn't quite what the statistical tests want. They want an actual table, and this is a data format in R, and the way we do that is with the table function, right? And so what we want to do is say, okay, do a table. It's similar to count here, count and spread all in one shot. And what we want to say is take dog name and breed and make a table of that, right? Or a crosstab. it just gives me an error because it doesn't know where dog name is coming from. So we could fix that by saying dog name $, or New York dogs $, dog name. Same thing with breed. So before, there is no dog name object, right? But if you prefix it with a $sign in the data set, it now recognizes, hey, this is an actual object. And we can make a table out of that, right? So that's one way you could do the table using the $sign. My preferred method, though, is to do what I was doing before, right? Where I had table and dog name. But you need to tell it a data set. And some functions will allow you to pass in a data set. So I've put the source code for table up here. And I'm looking to see if it allows us to pass in a data set. It doesn't appear to. I'm going to also look it up. It doesn't appear to allow us to pass in a data set. And a lot of functions are like this. So I've just gotten into the habit of wrapping them with, telling it the data set, which is New York dogs, comma, and then you give it the function and the names of the variables, right? So what this basically says is, okay, this table, go ahead and evaluate dog name and breed for it, but do it inside of this New York dogs data set, or with this New York dogs data set. And we run that and assign it to C tabs, and we get the same output that we got when I use the $sign method. Whatever method you're more comfortable with. The second method here probably requires less typing in the long run. But. All right, now we can perform our test of significance. And there's a built-in test right here. And that's part of the stats package, I believe. You can see if we put the source code in there. Yep, namespace comes from stats. And all we do is pass it in that cross tab that we just made here. And it does tell us, hey, there's definitely a significant difference between cells here. We don't necessarily know where they're at. It tells us degrees of freedom and then the chi-squared statistic as well. By the way, that p-value would be as if we evaluated against a alpha of 0.05. And so it doesn't really necessarily tell us where the differences are at. So in our plots, we know there's some differences, but where are those differences at? So the cross table function gives us a bit nicer output. And I would recommend these arguments here because it tends to give you too much and it can be overwhelming. The one thing we definitely want is standardized residuals because that will tell us where differences are at. So we run that. Let's actually get a little more real estate. I may need to shrink the size of the outputs above. We'll see. Let's stretch this a little bit. And we're going to want to know how to read this, right? So to figure out how to read this, you come up way up here, and it tells us what each of the rows are. So count is the first row. So we can see here, Bello and Chihuahua, 34 times that happened. Expected values, based on chi-squared results, we would expect that if these were done randomly, 36.5, roughly 37 of these would be Bella Chihuahuas, right? Chi-squared contribution, that's a bit less informative. The standardized residuals, though, at the very bottom here, are more informative, okay? So let's talk about those. You can see at the bottom, we still wind up with the same output for p-value, degrees of freedom, and the chi-squared test. But if we come up here, and I've shrunk down the size of the table output a little bit here, we can start looking at individual cells and the interaction between breed and dog name. And what we're looking for, we want to know where these big differences are. So those standardized residuals are a nice place to look. And we're looking for values, the absolute value that's greater than 1.96. Remember, that's one standard deviation, or two standard deviations outside of the norm. So we see that here, Chihuahua, a disproportionate number of Chihuahuas are indeed named Lucky. And a disproportionate number of Chihuahuas are not, so a negative standardized residual below 1.96. Or negative 1.96 are not named Max. So we can see that those two cells are definitely a place where there are big differences in what we would expect if things were random. Nothing else really jumps out too much. We do see Yorkshire Terriers named Bella approaching that 1.96 mark. So now we know at least two places, Lucky and Max for Chihuahuas, where there is indeed a difference that we can talk about in the groups. So our omnibus test for chi-squared tells us indeed there is a difference in these groups somewhere. And then the standardized residuals tell us where those differences likely are. How do I write this up? So I also wanted to give an example of how we could write this up in APA 6 style. Andy Fields in his book also gives some examples of how you would write up a chi-squared. So I think it's useful to understand how we could write that up. So a chi-squared test of independence, and here I have boilerplate, by the way. A chi-squared test of independence was performed to examine the relation between x and y variables. So dog name and breed. The relation between these variables was significant, so in this case it was. We rejected the null hypothesis. We have chi-squared, and here I have a caret too. You'd probably want to use an exponent or a superscript if you're actually writing this up. And then your degrees of freedom here, and we can see degrees of freedom is 9. And in the readings, it shows you how to compute the degrees of freedom as well. And then here you have the chi-squared value, which is 21.4. We'll round it one significant digit. Then the p-value here, we'll say p is less than 0.05 because that was our alpha level. And then we can talk about some attributed differences in plain words. So I come up here, and so Chihuahuas was really where the differences lie. We could say this overall difference can be attributed to Chihuahuas named, and we saw the big difference in Lucky and Max. Lucky and Max. And we could say something along the lines. Chihuahuas named Max appeared to be underrepresented for what would be expected, while those named Lucky had an over-representation of what was expected. Okay, so that's some boilerplate for how you could write this up. Andy Field also gives some example, and you can play with this wording a bit. But the important things to discuss are the omnibus overall test difference, report on it, what it is, the variables you'll be talking about, what the test was, chi-squared, the degrees of freedom, which is 9, the test result, the p-value, and then you want to give a bit of practical write-up of where these differences were at. You could also augment this with odds ratios. As an effect sizes, I would really encourage that, and Andy Field talks further about how you can do that as well. Let's look at one more example, just the test. I think we went through enough of the other things. So the Carnegie data set, and this comes from the Carnegie classifications, right? So it's a pretty large data set, but there's two interesting variables, so control and IC level. And let's do a crosstab of those. You can get a sense, even if you don't know exactly what those mean, when you actually look at the labels. So control is private, for-profit, private, not-for-profit, and public, right? And we see IC level, basically that's, are they a 4-year institution? Are they basically a 2-year institution? And we can see that, hey, there are a lot of public schools that are 2-year institutions. Not that many private for-profits do that. So you can see a flip here, basically, in the numbers. So there might be some interesting differences there. And in private, not-for-profit, wow, definitely a huge difference there. So it looks like private not-for-profits don't even bother with 2-year type colleges. Let's see if that hypothesis is kind of true. Is there a differences in the way that these groups are distributed if they were randomly distributed? And we see a very large p-value. And we can see here that it's using scientific notation. If that annoys you, you can do options, sci-pen equals something large. You could even go like 99. Let's see. Oh, actually, that's to the negative 237, so we'd have to go even larger to not do that as scientific notation. And now we look at the output, and that's still pretty unwieldy. It's pretty near 0. So we can see that these distributions are not likely by chance. We can see pretty large standardized residuals. As we said here, public, 2 years, huge standardized residual, so it's not happening by chance. Again, private not-for-profits, huge negative residual, not by chance. So we can see really very large standardized residuals in the expected values. So this tutorial should show you how to get started with the chi-squared testing. This should augment what you've learned in Andy Field's book, and I haven't shown everything that Andy shows here, including things like odds ratios and such for effect size, but this should get you started with doing chi-squared.